Hi, in this video we are going to go through some worked examples finding eigenvalues and eigenvectors of a matrix. So let's just jump right in. Start with the problem shown here. Can we find the eigenvalues and a basis for each eigenspace for this matrix here? I recommend that you pause your video, try to work through this problem on your own, and then resume to follow along the worked solution. The first step of this sort of problem is always to find the eigenvalues, which are the roots of the so-called characteristic polynomial, the determinant of lambda times I minus a. So let's see how we approach this in this problem. We start with our matrix A and construct lambda I minus A. I should note you can also form A minus lambda I and find the determinant of this matrix. The answer will be the same up to a sign, which is irrelevant when we're trying to find the roots. So the matrix that we're trying to find the determinant of will always have this form with lambda minus something on the diagonals and no lambdas occurring on the off diagonals. We evaluate this determinant. We can do this using cofactor expansion along the first row here. So our first term has a leading factor of lambda minus third multiplied by the determinant that's left after we delete the first row and the first column, this determinant shown here. For the second term, we have a coefficient of 0, which means we don't even have to worry about the determinant. And then the third term is negative third, so plus negative 1/3. Remember the signs here will be plus, minus, plus. So plus negative 1/3 multiplied by the determinant that we get by crossing out the third column in the first row, which is this one here. We then evaluate these. So our first term, we still have our lambda minus a third. Then we multiply by lambda minus 6 times lambda minus a third minus 0 times 0. So that gives us our piece here. Drop the 0 term. Minus 3 times 0 minus negative 3 times lambda 6. Where do we go from there? Almost always in this sort of problem, we're then going to have to go on to a step of simplifying the expression that we have to get us our final result, which can let us find our eigenvalues. There's various ways to do this. First of all, let's just clean up this expression, drop the zeros, multiply through. So this gives us lambda minus 3 times lambda minus 3 times lambda minus 6, lambda minus 3 squared times lambda minus 6. Negative 3 times negative of negative 3 is negative 9 times lambda minus 6. At this point, we see that we have a lambda minus 6 in each term, so we can factor that out, leaving us with lambda minus 6 times lambda minus 3 squared minus 9. Multiply out this, expand this into lambda squared minus 6 lambda plus 9. Then this plus 9 and this minus 9 will disappear. We're left with an almost complete form. We notice we have a lambda in both of these that we can factor out. When we do that, that's going to leave us with another lambda minus 6. And so our final expression, simplified down for the characteristic polynomial, is lambda times lambda minus 6 squared. The eigenvalues are the roots of this characteristic polynomial, that is, the solutions to this expression being equal to 0. Lambda times lambda minus 6 squared will be equal to 0 either if lambda is 0 or if lambda is 6. That gives us our two eigenvalues. We then move on to find eigenvectors. For eigenvectors, we have to find a basis for the eigenspace. Remember, there's actually an infinite number of eigenvectors associated with each eigenvalue. They may lie along a line, they may lie on a plane, or so on, because they really are just the null space of a certain matrix. The eigenvectors are the vectors that are solutions to lambda I minus a equals 0, the null space of this matrix. We characterize this with a basis for a linearly independent set of eigenvectors. We do this for each lambda. Start with lambda equals 6. Plug that into our expression for lambda I minus a. This is going to give us 6 minus the diagonals everywhere on the diagonal. So this will give us 3. 6 minus 3 is 3. 6 minus 0 is 0. And 3 minus 3 is 3. And the negative of a is on the off-diagonal elements. Once we have this, we just find our null space basis the same way as we have in multiple examples previously. Perform elimination to a reduced row echelon form and read off our answers. Turns out that the third row was a scalar multiple of the first, and the second row was already all 0. So our first step gives us 2 0 rows. We simply scale this so that we have a pivot of 1. This is a reduced row echelon form. We have 2 free variables, x1 and x2, which means we have 2 basis vectors, one with our first free variable equal to 1, and one with our second free variable equals to 1. For the pivot, and the others equal to 0, of course. For the pivot value, the pivot column is column 1. The pivot value we read off from the appropriate column, negating the answer. So we get a 0 for the first case and a +1 for the second. These two vectors, these null space vectors, are a basis for the eigenspace associated with lambda equals 6. We had another eigenvalue, an eigenvalue of 0, so we do the same thing. We plug in lambda equals 0 into lambda I minus a. This is just going to give us negative a. And again, perform elimination. This last row is identical to the third, so it becomes 0. This is an upper triangular form. We scale each row to give us 1s. And we notice we already have a 0 in the position above this pivot. And so we are already in our upper echelon, or our reduced row echelon form. We have 1 free variable. This means we will have 1 basis vector. We set that free variable, x3 equals to 1. And we read off the pivot entries by looking at the appropriate entries of this column, negating each one. So we get -1 and 0. This is our basis for the eigenspace associated with lambda equals 0. In this problem, the lambda equals 0 has an eigenspace that's a line. Lambda equals 6 has an eigenspace that's a plane. All right. Let's go on to another example. Let's take a look at this matrix. The last matrix had a lot of zeros, was symmetric, had a lot of simplifying factors about it. This is a kind of more, a less trivial example, if you will. Once again, I recommend that you pause the video, try to solve the problem on your own, and then resume to follow along with the worked solution. All right. Once again, we start by trying to find the characteristic polynomial. You will notice that in this general case where we haven't sort of constructed the problem to be particularly easy to work with. It does actually involve a fair bit of arithmetic. It's straightforward, however. There's nothing really technically complicated about this process. It's tedious. So plug in unknown lambda into the expression lambda I minus a. The diagonals will be all of the form of lambda minus the diagonal entries of the original matrix. The off diagonals will be the negative of that matrix. Once again, you can get an equivalent result by formulating the determinant as lambda minus a minus lambda I. You'll get the same final result. Expand along the first row with cofactor expansion. There's nothing sort of more obviously easier to do here, so this is somewhere we can start. Lambda minus 3 multiplied by the determinant left when we get rid of the first row and the first column. Then the second term, minus 1, we go plus, minus, plus, when we're starting with the first row, minus 1 times the determinant that we get when we cross out the second column in the first row. And then our third term plus negative 1 times the determinant that we're left with when we cross out these terms. First row in the last column, this determinant here. Expand these through. We have lambda minus 3 multiplied by lambda plus 5, lambda minus 2, minus negative 6. Negative 1 times negative 7 times lambda minus 2 minus negative 1 times negative 6 is plus 6. Minus 1 times negative 7 times 6, which is negative 42, minus negative 6 times lambda plus 5. Once again, we approach this first of all expanding and then simplifying this expression. So multiply through this, I'll change the color to make it a little easier. Multiply through this product gives us lambda squared plus 3 lambda minus 10 plus 6 for this next piece here, which will further simplify into lambda squared plus 3 lambda minus 4 as we leave here, leaving this first term in front. Minus 1, expand this, negative 7 times lambda minus 2 is negative 7 lambda plus 14. Minus 6, which simplifies down to negative 7 lambda plus 8 as we have here. And minus 1, negative 42 minus negative 6 times lambda minus 5 is plus 6 lambda plus 6 times 5, or 30. Then the negative 42 and the 30 simplify down into 6 lambda minus 12. We can take a look at this, and there's no obvious term to factor out of this expression. So instead of factoring here, we're going to start by expanding each of these terms out, and then once again simplifying down all of the remaining terms. So lambda minus 3 times lambda squared minus 3 lambda minus 4 is lambda times this, which gives us lambda cubed plus 3 lambda squared minus 4 lambda, minus 3 times this expression, minus 3 lambda squared minus 9 lambda minus plus 12. Then the next term, negative 1 times negative 7 lambda becomes plus 7 lambda minus 8, and negative 1 times 6 minus lambda becomes negative 6 lambda plus 12. Then it's really just a matter of simplifying. We have one term with a lambda cubed, that's this. We have a 3 lambda squared, and a negative 3 lambda squared, those disappear. We have a negative 4 lambda, a negative 9 lambda for negative 13, plus 7 lambda gives us negative 6, and another negative 6 lambda gives us negative 12 lambda. Finally, the pieces with no lambda, plus 12, minus 8 is plus 4, plus 12 is plus 16. And so we have our simplified form of our characteristic polynomial. And a bit of tedious algebra, but nothing technically complicated. We want the roots of this now. You can look up the general form for the solution of a cubic. This is a cubic polynomial, and you can apply that. You can try to use a computational system to give you the roots of this. I think it's worth getting familiar with some of the more analytical techniques to factor polynomials. And so let's go through how we might approach this problem if we were working without a calculator, without a reference guide, and we just wanted to do this simply on pen and paper by ourselves. One of the features of polynomials of any form, anytime we have some x to the n and then plus some series of terms plus some ending a0, notice we have a coefficient of 1 in front of this first piece. If we are going to have an integer solution, it has to be a whole number factor of this last term. This is just a kind of think about it as we factor out a polynomial into something of x minus something else, x minus something else. The term that is left at the end with no x's comes from multiplying these last entries, which are the individual factors. And so they have to multiply out to give us this answer. So that gives us a limited number of possible integer solutions. We can ask, does this have integer eigenvalues? So we might check, actually I should add in here, plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 16. Right? 1 obviously isn't going to work. That would give us 1 minus 12 plus 16, which is not 0. I should say if there's integer roots here. Negative 1 isn't going to work. That's going to give us negative 1 plus 12 plus 16. Also doesn't give us 0. But think about 2. 2 gives us 8 minus 24 plus 16. 8 plus 16 is 24, so this does indeed give us 0. Lambda equals 2 is a root to this equation. Lambda minus 2 equals 0 is a factor of this. You could keep testing and ask, does negative 4 work? Does negative 2 work? Does plus 4 work? Does minus 4 work? Does 8 work? Does 16 work? And so on. Some of them it should be clear that it's not going to work out. The 16s are going to be a really, really big number here, and there's no way we're going to eliminate that large number with the remaining terms. But you could keep trying. The other thing that you can do is try to factor out this term that we've already found. So we know lambda minus 2 equals 0 is a factor. Lambda equals 2 is a solution. And so let's factor that out. We start with our cubic, and we say that this is going to equal lambda minus 2 multiplied by some quadratic. That's how we always sort of factor a cubic. How can we figure out what this a and this b are going to be. We know that the leading coefficient of lambda squared has to be 1 because we have a coefficient of 1 here. Well, let's look at the last piece, right? The last term, 16. This 16 has to come from the product of -2 with b, so we have -2b equals 16. This tells us b has to be equal to -8. So that's partly filled in our polynomial here. We now have this a term remaining. What happens when we multiply this through? Which terms will have just a lambda? Right, so we have this -12 lambda. Well, there will be one term that has a lambda that comes from lambda multiplied by -8, -8 lambda. There will also be a term that gives us a single lambda that comes from -2 multiplied by a lambda, -2a lambda. And these together, -8 lambda minus 2a lambda has to equal -12 lambda. -2a lambda has to be -4 lambda. A has to be 2. That gives us a factoring into our one root that we found kind of by just testing the possible integer solutions, a quadratic that we have from factoring out the polynomial, and then we can factor this. We're looking for a pair of numbers that multiply to give us -8 and that add together to give us 2. A pair of numbers that will do this will be 4 and -2. Right? So our factorization is lambda plus 4, lambda minus 2. So we actually see that that lambda 2 that we had found here was a repeated root, lambda minus 2 squared multiplied by lambda minus 4. If we were going through the testing approach, we would have had to test -2 plus 4. We would have found an answer at -4, but we still wouldn't have been known that we could stop because we would have only had 2 roots. And so we'd have to go checking others just to make sure. The factorization approach is often a better strategy than just testing over and over again. Once we've factored, we can plug that in to our sort of expression of our characteristic polynomial equals 0. We'll get 0 either when lambda equals 2 or when lambda equals -4, our eigenvalues. This was a bit messy, involved a fair bit of algebra, factoring out a polynomial, but we got our answer. Once we have our eigenvalues, we apply the same standard approach to find a basis for the null space of lambda I minus a with a set lambda. Let's start with lambda equals -4, the one that was largest in magnitude. We express lambda I minus a. -4 minus 3 is -7. -4 minus -5 is +1. -4 minus 2 is -6. That's the diagonal entries. And the off-diagonal entries are just the negative of the off-diagonals in A. Again, we can always do this A minus lambda I if you're more comfortable doing it in that form. So once we have this, we note that the second row is a scalar multiple of the first, so it just sort of immediately sort of subtracts out to give us 0. I'm going to do something a little bit non-standard here in following elimination, just to make the arithmetic a little easier. If I wanted to eliminate using this, I have to divide through this number by 7, and then I'm going to have terms here that involve sort of sevenths. To avoid doing that, I'm going to start by exchanging these 2 rows, putting the one with a 1 up in the first row, move the 0 row down to the bottom, and our second row here. We're always allowed to exchange rows during elimination. And this then gives us a nice one pivot, which is easy to work with. We add 7 times the first row to the second. 7 minus 7 is 0. Negative 7 plus 1 is negative 6. 7 minus 1 is plus 6, giving us this matrix. Now this is now a echelon, an upper triangular form. Divide the last pivot by 1 to give us our form that has our 2 pivots equal to 1, but then we need to eliminate upwards to 0 out this row, add the second row to the first, gives us an upper echelon form. One free variable means we're going to get one vector out of this. We set that free variable equals to 0, and we find the pivot variables x1 and x2 by negating these entries 1 and plus 1. Our single basis vector for eigenvalue equals -4 is 0, 1, 1. This eigenspace is a line. We do exactly the same thing for lambda equals 2. Plug it into lambda I minus a, gives us 2 minus 3 is -1, 2 minus -5 is 7, 2 minus 2 is 0. That's our diagonal entries here. Off diagonals are just the negatives of a. And the same approach. Here we already have a fairly easy to work with pivot, so we subtract 7 times the first row from the second row and 6 times the first row from the third. This ends up giving us 2 identical rows in the second and third row. So our next elimination round will give us a 0 row in the bottom. We can scale this one to give us a 1 in our pivot and eliminate upwards to give us our final upper echelon, reduced row echelon form here. This is duplicated, so we don't need to bother. Oh, sorry, not quite duplicated. Sorry about that. This was not that piece here was not quite an echelon form, a reduced row echelon form, because of the -1 here. So we take one extra step of multiplying this row by -1 to give us our reduced row echelon matrix shown here. Once again, we have a single free variable. That is that's not our free variable. Our pivots are here and here. Always be careful about sort of walking through, making sure you know which your free variable is. Column 2 gives us our free variable. We find our single vector by setting that free variable equal to 1 and finding the pivot entries by looking in the corresponding column, -1 and 0. We negate those to get 1 and 0. Our single basis vector for lambda equals 2 is 1, 1, 0. This eigenspace is also a line. We had 2 eigenvalues. We found eigenbases for the eigenspaces for each of them. We're done with this problem. Let's go on to one last problem. We saw that case here, a 4x4 case. We saw in the previous example that even 3x3 matrices can get pretty messy if they're not constructed in a way to make them easily solvable or by hand. This is an example of a 4x4 matrix, but one that has been constructed to be fairly easy to work with. I recommend that you pause your video, try to solve this problem on your own, and then resume. Okay. As always, we are going to start by finding the roots of lambda I minus a. So we start off by constructing that matrix. Lambda I minus a is always going to have on the diagonals terms of the form lambda minus the diagonal entries of a. And the off diagonal entries here, actually these should all be negated because because they should be the negative values of A. And we want to evaluate this determinant. Well, how do we do that? This is easy because we have an upper triangular matrix. When we have an upper triangular matrix, the determinant is simply the product of the diagonals. These always give already factored eigenvalue characteristic polynomials. The product of the diagonal terms are all in a form lambda minus something. That means we directly get a nicely factored characteristic polynomial. The eigenvalues are just these entries. This actually is a general result that the eigenvalues of an upper triangular matrix are always just the entries on the upper triangular, on the diagonal. So eigenvalues in this case were easy to find. We have 4 of them though, and so in order to find eigenvectors, we're going to have to apply, find a null space for 4 different matrices. Right? We plug in lambda equals 1 to our expression of lambda I minus A. Off-diagonal elements are just the negatives of the off-diagonals, and the diagonal elements 1 minus 1, 1 minus 2, 1 minus 3, 1 minus 4. So this is the matrix that we're working with. Go through elimination. Here it's kind of interesting. We start off with a column of all zeros. This tells us that right away we know that this first column is free. There's no pivot. That means we shift over to the next row using this as a pivot to eliminate downwards. And sorry, I've done kind of a non-standard approach here, if you will. I've started at the bottom just to simplify things a bit. You can go through standard approach also, but because we're in an upper triangular form, you might say, let's start at the bottom and just use back substitution. And if we do that, we start with our -3. We scale that to give us 1 and eliminate upwards to eliminate all of these. This will just zero out this whole column. Then we move up to our next pivot, -2. We scale it to be a -1 and eliminate upwards. Because we had a 0 here, this also just zeroes out the remaining entries. We then move up and over, again scale to give this +1, eliminate upwards. Because everything else was 0, it just makes this piece disappear. And we can, at that point, now move our 0 row down to the bottom and everything up. And this gives us a form that's a reduced row echelon form. We also could have gotten this using standard forward elimination just as easily. As we noted at the very beginning, this first column is all zeros. It has stayed all zeros. This is our free variable. In order to find a basis for the eigenspace, we set that value equal to -1 and fill in the pivot entries from the corresponding entries of that column. They're all zeros. So 1, 0, 0, 0 is our single eigenvector, our single basis for the eigenspace. Our eigenspace is a line. Same approach for each of our other eigenvalues. Starting with lambda equals 2, the off diagonals become the negatives of A. The diagonals are 2 minus 1, 2 minus 2, 2 minus 3, and 2 minus 4 for these entries here. And then go through elimination. We start with our first pivot. It's already taken care of. We move over. This is a free variable, not a pivot. Move to our, apologies here. I forgot that I've structured all of these in a way that I've been doing the backward substitution. You can take this approach if we sort of work through, if we were taking the forward approach, we would move over now to this next piece as a pivot. We would scale it to give us 1 and 1, eliminate downwards to get rid of this, to give us a 2, and so on. This would work perfectly fine. We can also go in the sort of reverse direction here and start from the bottom, recognizing that we're in an upper triangular form. Scale and eliminate upwards gives us a column of 1, all zeros. Move over, we already have a 1. Eliminate upward gives us our column of all zeros. Move over and up, and we have our single piece. We're in essentially a reduced row echelon form. We should have taken one extra step of moving the 0 row down to the bottom. And this gives us our final reduced row echelon form. A single free variable in position 2. We set that equal to 1. And we draw our pivot entry out of this column, 1, and the rest zeros. Our single vector for basis vector for lambda equals 2 is 1, 1, 0. We can continue doing the same thing. Lambda equals 3. Off diagonals are the negatives of A. The diagonals are 3 minus 1, 3 minus 2, 3 minus 3, and 4, giving us 2, 1, 0, 1. This is the matrix we're working with. We'll start recognizing this is an upper triangular form with back substitution. Eliminate upwards to give us 1 and all zeros. Move over to our next pivot. We had a 0 row up here, so our next pivot is all the way over here. Eliminate upwards. Here everything isn't just all simple zeros. We add the second row to the first. That gives us a 0 in this position, but -1 plus -2 gives us a -3, not a 0. Scale this row by dividing through by 2, gives us a 1, 0, and -3 halves. Again, I probably should have swapped these rows here. We have 3 pivots. 1 free variable. Our free variable here is in position 3. We set that value equal to 1, and we read off the pivot entries from the appropriate columns here, negating to give us 3 halves and 2. We could leave it in this form for our basis for our sort of lambda equals 3. It's often simpler to work with whole numbers, and so I've just multiplied this vector by 2 to give us a all whole number basis vector for our eigenvalue 3. Same thing for our lambda equals 4. Plug it into this expression. Off diagonal entries are the negative a's. The diagonal entries are 4 minus 1, 4 minus 2, 4 minus 3, 4 minus 4, or 3, 2, 1, 0. And same approach. Last row was already zeros, so our first pivot is actually this one. Eliminate upwards. Once again, because we have non-zero entries here, it's a little bit more involved in elimination. Add twice the third row to the second. -2 plus 2 is 0. -2 plus -6 is -8. -1 plus 1 and -1 plus -3 gives us 0 and -4. Up and over to our next pivot. Scale, divide through by 2. And then eliminate upwards. Add the second row to the third. -1 plus 1 is 0, 0 plus 0, -4 plus 4 is -8. Last step, scale, this should be a 1 here, to give 1, 0, 0, -8 thirds for this row. one free variable in our x4 position, so we set that value equals to 1, and we read off the pivot values by negating the entries here, 8/3, 4, and 3. We can leave it in this form for our eigenspace basis, or, as we did in the previous case, multiply this whole thing by a constant factor of 3 to give us 8, 12, 9, 3 as a basis vector with whole numbers. All right. So what we've gone through there has been 3 examples, starting with a matrix, carrying through to find eigenvalues by determining the characteristic polynomial, factoring it to find the roots, and then using those eigenvalues, the roots of the characteristic polynomial, plug them into our form lambda I minus a, and find a basis for the null space. Right? This is how we find eigenvalues and linearly independent eigenvectors, or a basis for the eigenspace of a general matrix. Things get messy, things get tedious working through things by hand. In the real world, we tend to solve these problems computationally, but you should now have had a feeling for how you can work through these kinds of problems just on pencil and paper. In an accompanying second sort of worked example video, we'll go through some more uses of this these eigenvalues and eigenvectors to perform an eigenvalue decomposition and to use those to simplify solving certain kinds of problems. Thank you, and goodbye.